Welcome back. In this video, we are going to talk about the enthalpies of reaction and formation. So in the last video, we started on really explaining Hess's law and how we can exploit the fact that enthalpy is a state function. And so we're going to build upon that with some specific types of enthalpies. Okay, so enthalpy of formation. When we write something like zinc Cl2 aqueous, we can go into a table. This is going to be in the appendix in your textbook, that there is a table of delta H of formation values. And in this table, you can find zinc chloride aqueous, and you can find that the delta H of formation for this species is a negative 63.17 calories per mole. Your book is probably going to have these in kilojoules, but other tables you might find in energy units of calories. Now, our first question is really, you see there is this little degree sign on this delta H. And the first thing we have to figure out is, what does that mean? What it means is that all compounds and elements are in their standard state. So compounds are in their pure form. That means that they're in the form that they would exist in nature, how we would find them. The temperature is at 25 degrees C or 298 Kelvin. All solutions are 1 molar. The pressure is 1 bar. And everything is for 1 mole of compound. Okay, so what do we mean by the enthalpy of formation? The enthalpy of formation is really looking at the energy of the elements in their standard state, so the purest form. And we are looking at how much energy is involved when these elements combine and form a compound. And so, for example, water is formed from hydrogen gas and oxygen gas mixing together, and that reaction is exothermic. And so that tells us that water liquid is more stable, has a lower energy than hydrogen gas and oxygen gas in their elemental forms. Now, the more negative the enthalpy of formation, the more stable the compound. Okay, so now, how do we relate enthalpies of formation that these are given to us in a table in the appendix? How do we use those to get to useful things like and real things like the enthalpy of reaction? So if we have the generic reaction where some number of moles of A reacts with some number of moles of B to form a moles of C to form some number of moles of D, we've covered how the delta H of reaction is going to be the products minus the reactants. And what we can do is we can use the delta H of formation for the products and the reactants in order to calculate our delta H of reaction. And so really what we are doing is we're starting with the reactants and we're going to dismantle them. We're going to break all of the bonds, and then we're going to form all of the bonds in the products. Now, this is the point that I need to remind you that breaking bonds is always an endothermic process. And making bonds is always an exothermic process. So fun story, whenever I took thermodynamics as an undergraduate, there was a final exam question that was labeled in order to pass or fail the class. Breaking bonds are blank, making bonds are blank. And we had to know that breaking bonds was endothermic, making bonds was exothermic, because this is a very key part of thermodynamics. And really, we're looking at the difference between the energy required to break bonds versus make bonds. Okay, so how do we put this together? This is a Hess's law problem. And so if we want to find the enthalpy of reaction, what we can do is we want to work with our products minus our reactants. And so if we work to find the enthalpy of formation from the table. So in the table, when we see the enthalpy of formation of NO gas, that means that we're going to take N2 plus O2 to form two NOs. Now, remember that the table gives us the delta H of formation for 1 mole. In this example, we're making 2 moles. And so the table is really 1/2 N2 plus 1/2 O2 goes to form NO. But in our reaction, we don't want just one NO, we want 2 of them. And so what we're going to do is we're going to multiply this delta H of formation by 2 to be able to get 2 moles of NO. And likewise, we can make water liquid from 4H2 and 2O2 to make 4 H2Os. Now, in the table, it's going to be H2 plus 1/2 O2 forms H2O. And since we multiplied this reaction by 4, we also have to multiply the delta H of formation that we find in the table. Now, we've got a typo here. This should be liquid. Notice it's key that the state that you find in the table and the state that you are using, they need to match. And we'll talk about why that is in a little bit. And then we can do the same thing for the reactants, but this time, so in the table is listed as forming the compound from its elements. And so the compound that we're looking at is always a product. So when we want these to be reactants, we have to flip the sign of our delta H, just like we did in the other example on the last video. And then if we add these things together, we'll see that our N2s cancel out, our H2, I've got 1 there, I've got 3 there, so that takes care of 4. I've got 3 O2s, 2 and 1, and it leaves me with 3 sulfur. Notice that I didn't worry about my sulfur in my reaction because it's already in its elemental form, it's already in its standard state. So now my delta H of reaction becomes the sum of all of my delta H's of formation all together. And so we can simplify this down to that the delta H of reaction becomes the sum of the moles times the delta H of formation minus the reactants, the moles times the delta H of formation. Now, notice that the heats of formation do depend on the phase of the substance. So if we talk about calcium chloride solid, we get a negative 795.80 kilojoules per mole from our table. But aqueous is 877.15 kilojoules per mole. So let's think for a moment as to why these are different. And this should start to remind you of a certain exam question that you may have done. We basically are working with a mixing sort of situation. And so to start out with, we have calcium chloride in solid in water. And as time goes on, that calcium chloride dissolves throughout the water and is mixed. And so the energy, the entropy especially, of this solution changes because we have a mixing situation going on. And so the number of microstates of the products are much higher than the reactants if we think about going from CaCl2 solid to CaCl2 aqueous. So now, if I dissolve calcium chloride in water, do we think the beaker will feel hot or cold? Well, the answer is going to be hot. Because really we can think about this as products minus reactants. And so if we have a negative 877.15 kilojoules per mole minus a negative 795.80 kJs per mole, our answer is going to be a negative value, and that is exothermic, which means that energy is going from the system to the surroundings. And in this case, our hand, our feeling, is the surroundings. And so it's going to feel hot. Now, let's think about a different example. When we have ammonium nitrate in water, is the beaker going to feel hot or cold? So we are going from our product is dissolved, and so we have a negative 337.5 kilojoules per mole for our products, minus our reactants is a negative 365.6 kilojoules per mole. And so my delta H is going to be a positive value, and that means that this is endothermic. And so that means that energy is moving from the surroundings to the system. And so our hand is the surroundings, and it is going to feel cold because the energy is leaving it. So now if we think about the microscopic picture of dissolving ammonium nitrate, what does this tell us? We start with our NH4NO3, solid with water around it, and we go to our water with ammonium nitrate dissolved. We would normally think that our gut reaction would be more microstates. And this is true because we're really looking at delta G equals delta H minus T delta S. So remember that the spontaneity becomes a competition between the energy and the entropy. And so since this dissolves, it's an ionic species, so delta G is negative. We know that delta H is positive. This tells us that delta S has to be positive. In order for this to be endothermic, it tells me that it has to tell me that there is a lot of structure involved in the solid. And so that means that it's going to require a lot of energy to be able to break up those ions and dissolve them into water. And that energy is going to be more than what is gained from the entropy and from any structural formation that happens within the water. And so that tells me that these ionic bonds are strong.